Welcome to Algebra 2. Today we got section 10.2, independent and dependent events. All right, so in this chapter we're looking at probabilities. Again, we talked about those in section 10.1 as being a number between 0 and 1. So 0 is a probability that that event will not happen, and 1 means that it definitely will occur, something in between. Well, what if we're talking about more than one event occurring? Well, this is where we typically think of our most common types of probability problems: coin flips and dice rolls and drawing cards out of a deck of cards. And here we need to decide, does one event occurring have an effect on the other one? And that's really what we're trying to say here. If there is no effect between, we're referring to those as independent events, whereas if one event happening affects the next event happening, then they're dependent events. And typically where dependent events come into play is when we involve replacement. So if we're drawing out of a deck of cards and we draw one card and then replace it, then our events are independent because we've restored that deck of cards back to its full starting value. Whereas if we keep the card out of the deck, then we have not replaced it. So I have a new deck that I'm drawing from for my second event. In other words, they depend on each other. It changes the sample space. So just to get started, we've got a couple of situations here. We just need to decide, are they independent or dependent events? So the first one, 2 dice are rolled. I want you to just come up with an idea real quickly. Do you think that's independent or dependent? And hopefully we quickly decide here that if we roll 2 dice, well, the way one die will land has no effect on how the other one will land. So those are definitely independent events. Okay, next, 2 cards are drawn one at a time without replacement. Well, now if you think about this, if I have a deck that has 52 cards in it and I draw 1 card out, I have changed the deck. Since I don't replace that card, I have changed the deck. So when I go to draw another card out, I'm drawing from fewer cards. I have not replaced it. That means that that second draw depends on what the first draw was. These are dependent events. All right, so how does this factor into our probabilities? This is one of our first big vocabulary understanding moments for probabilities. When we have multiple events occurring, I want you to use the word "and" to describe that situation. I want this and this to happen. Because when we're dealing with probabilities, "and" typically means multiplication. So if they're independent events, one has no bearing on the other. So to find the probability of one event and the other event, I just multiply each of their probabilities together, knowing that one will not affect the other. So the probability of A and B, sometimes that is shown as this, A and B. It kind of looks like a lowercase n without the little tail on it. That means an intersection. Think about a Venn diagram. It's a place where they overlap. Just a little notational thing. It's just the probability of the first times the probability of the second, and just multiply those together. Now, if they are dependent events, think about that deck of cards where we don't replace the card afterwards, then our probability of A and B is the probability of A times the probability of B given A. So that little bar there, we can read that as given. So let's just run through a quick sample and say, what's the probability of drawing a jack out of a deck of cards if I don't replace it, and then drawing a second jack out of the deck of cards afterwards? So probability of jack and jack would be the probability of drawing a single jack out, which there are 4 jacks out of 52 possible cards, and then after I've taken that 1 card out, now there are only 3 jacks remaining, and there are only 51 cards left in the deck. So you can see probability of B given A, it has adjusted the sample space and adjusted my desired outcomes. So we have a different fraction entirely with that second case here, dependent events. All right, well, maybe just to make this a little bit clearer, let's go back to independent events. Let's say we were trying to get the probability of Jack and Jack if I replace the card. That would be independent because I'm going back to that same sample space, that entire 52 card deck. Well, this would be 4 Jacks out of 52. Then I replace the card and draw again, 4 Jacks out of 52 again. They won't always be the same number, but you can see that I have the same sample space, those independent events. One has not had a bearing on the other. Just a little example. All right, so to start off this lesson, we are just going to decide whether or not these are independent or dependent events. So for problem number 4, we roll a 6-sided die and we flip a coin. 2 events. So event A is you get a 4 when you roll the die. Event B, you get a tails when flipping the coin. So think about this situation. If I roll a 4, does that make it more likely or less likely that I get a tails when I flip the coin? Definitely not. So these are dependent. Oh, sorry. Definitely not. These are independent. Okay, and our reasoning is that the outcome of event A, it doesn't affect the outcome of B. So if I were to roll and get my 4, that doesn't make it more or less likely that I will get tails flipping the coin. The coin flip is independent of the dice roll. Number 6, here we've got 22 novels on a shelf. Okay, maybe the titles or the genres have all been obscured. You randomly choose a novel, then put it back. Then you randomly choose another one. Okay, so the put it back, that's a key point of this problem. They are replacing that book on the shelf. So event A, you choose a mystery novel. Event B, you choose a science fiction novel. Well, those are going to be independent events again. Because the likelihood of event A happening is not affected or not affecting the likelihood of B occurring. And it's because we put that book back on the shelf. We had a certain probability of drawing a mystery novel and a certain probability of choosing a science fiction novel. And since we put the book back, there was no change in how many books we started with. It was still out of 22 books. So choosing a mystery novel and putting it back does not change our likelihood of getting the science fiction novel the second time. So that was the explanations. The outcomes and likelihoods, I guess, are not affected by, the second event is not affected by the first one. So here in number 8, we have 1 red apple and 3 green apples in a bowl. Randomly select 1 apple to eat now and another one to take with your lunch. Use a sample space to determine whether randomly selecting a green apple first and randomly selecting a green apple second are independent events. Okay, notice it says 1 apple to eat now, and then you take another one for lunch. All right, it says use a sample space. So let's just kind of list out what are some possibilities that we could have. Okay, well, we could choose, maybe we choose the red one first, and then there's green, green, green left in the bowl. We could choose a green one first, then there's red, green, green left in the bowl. We could choose a green one first, and then green, red, green. And this is just kind of imagining drawing all 4 apples out. We could have a green first, green second, green third, and then the red one last. Now, we're only choosing 1 to eat now and then another one for our lunch. But we are not replacing the apple back in the bowl. Of course, we're eating one of them now. All right, so determine whether randomly selecting a green apple first and randomly selecting a green apple second are independent events? And the answer is no, these are dependent events. Because if we randomly choose a green apple first, that is affecting randomly selecting a green apple second. Because choosing a green apple first, that changes. Now we have a reduced number of apples left in the bowl. So randomly choosing that green apple first, and then randomly selecting a green apple second, well, there are fewer numbers of apples left in the bowl. So we have affected the outcome of selecting that green apple second. The probabilities have changed. All right, now we get to some of the actual equations with this. And I think this helps to make the problem-solving process much more clear. Okay, you're playing a game that involves drawing two numbers from a hat. There are 25 pieces of paper numbered 1 through 25 in the hat. Each number is replaced after it is drawn. Find the probability that you will draw a 3 on the first draw and a number greater than 10 on your second draw. And remember, we are replacing it. It is replaced. Okay, so we want the probability of 3 and greater than 10. Well, since we know we're replacing, we know it's independent. Every time we draw a card out, we're going to put that card back, so we're always drawing from the full 25 pieces of paper, the full hat. So I want the probability of a 3 times the probability of drawing a number that's greater than 10. All right, well, what's the probability of drawing a 3? Well, there's one card in the hat that's labeled with a 3 out of 25 possible in my sample space. And I could have 11, 12, blah, 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 all the way up to 25. There are 15 possibilities of numbers that are greater than 10. And since I replaced that first one, whatever it may be, there are still 25 numbers in that hat. So I still have a sample space of 25. Those are independent events. If I multiply those together, I get 0.024. Or we could say 2.4%. Right? Probability could be written as a decimal or a percentage or a fraction if we wanted to put it that way. It'd be 24 out of 1,000 we could reduce. But we want to make sure that our answer is between 0 and 1. And in this case, it definitely is. And you can see, not very likely that we get that very specific combination of cards. Okay, our next example, here we have a word game. Looks like Scrabble to me. We have 100 tiles, though, 98 of which are letters and 2 of which are blank. And if you've played Scrabble or a game similar to this, you turn all the tiles upside down and kind of shuffle them around. And then you draw tiles to kind of get your starting rack of letters to begin the game. All right, find the probability that both A and B will occur. Well, let's take a look. They tell us how many of each tile are in the top of the box here. Event A is that your first tile that you draw is a consonant. Then event B is that the second tile is a vowel. All right. Well, looking at these, and I have to do a little quick calculation here. I find that there are 42 vowels. There are 56 consonants. And then there are the 2 blank ones. So 100 total tiles, like they said, but just kind of separating those into A, E, I, O, U, and the other letters. So we want to find the probability of A and B. But they say you draw one tile and set it aside. You don't replace it in the box. You got to keep that one. So now I know that the probability of A and B, those are dependent events. So I've got the probability of A times the probability of B given A has occurred. All right, so let's figure out what those probabilities are. The first one, I draw a consonant. Well, there are 56 consonants out of 100 possible tiles to draw in the sample space. And the second one must be a vowel. All right, there are 42 possible vowels, but since A has already occurred, there are only 99 tiles left in the box. Okay, so we multiply those together. to find our probability that both events occur. And what I get is the decimal. Let me find it here. 0.2375, or about 23.8%. The problems go very quickly, but a lot of the interpretation is what takes time. So understanding independent and dependent, and then being able to set up that probability of this occurring, that's really important to understand how the language or the situation, the problem ties in with the math. The math is just multiplication. Okay, and our next example, number 20. Here we've got a bag that has 9 red marbles, 4 blue marbles, and 7 yellow marbles in it. You randomly select 3 marbles from the bag. What is the probability that all 3 are red when? And then they give us a couple different situations. A, you replace the marble after drawing it. And B, you do not replace. Okay, let's compare those two probabilities. So letter A, here we want the probability of red and red and red. And if I'm replacing them each time, those are all independent because I'm always drawing out of the full bag. Okay, the whole bag has 20 marbles total in it. Right, just adding up all those different colors that we have there to get the total sample space. What are we drawing from? So I know 9 of the 20 is my probability that I'm drawing a red first. Then I replace it, and now there are still 9 in the bag. I'm still drawing out of 20. That's my probability of getting another red. And for the third marble, 9 red marbles are still in the bag. We put them back each time, and there's still out of 20 marbles total. So that gives me 0.0911, or about a 9.1% chance or probability that we get 3 red marbles if we replace them each time. Letter B says, what if we don't replace them? So now we want, again, red and red and red. But this time, because I'm not replacing them, our values are going to change. So the first marble, there's 20 in the bag, 9 possible red ones. And then what is the probability of drawing another red given that I already have one of them out of the bag? Well, now there are only 8 red marbles left in, and I'm only drawing from 19 left in the bag. I kept that one out of the bag. I didn't replace it. And then the third one, now there are only 7 red marbles remaining out of 18 that are left in the bag. So you can see that now that these events are dependent, each successive draw depends on what happened before it. You can see that our sample space has changed and the number of outcomes has also changed. What we get for this one is 0.0737, or about 7.4%. So not surprisingly, as we draw more red marbles out of the bag, it becomes less and less likely that we'll draw another red out. Okay, and our final example, we're going to talk about these types of representations of data a little bit more when we get into 10.3. It's called a two-way table. All right, and what this is representing is tropical cyclones over a 12-year period. And then they've recorded how many of those were actual depressions, storms, or an actual hurricane. So this data, compiled over 12 years, can be used to help predict likelihoods of things happening in the future, probabilities. So letter A says, find the probability to predict whether a future tropical cyclone in the northern hemisphere is a hurricane. Okay, so that means what's the probability that out of everything that happened in the northern hemisphere, we end up with a hurricane? So when we're looking at this, what we're looking at is hurricane over everything in the northern hemisphere. Okay, so we're looking at all those different data points. And how many hurricanes do we have? And remember, we are in the northern hemisphere only, so that southern hemisphere stuff doesn't matter. Another way of reading this is, what's the probability that we have a hurricane given that we're in the northern hemisphere? Okay, so in the northern hemisphere, we had 379 hurricanes out of how many total tropical cyclones do we have in the northern hemisphere? Well, if we add up 100 plus 32, or 342 plus 379, we get 821 occurrences, and that works out to the probability of a hurricane in the northern hemisphere of 0.4616, or about 46.2%. Okay, now let's compare that to part B. Again, we want to make sure that we are choosing the correct sample space and the correct desired outcome. The probability to predict whether a hurricane is in the southern hemisphere. So now our sample space and our outcome are different. Now we're looking at total number of hurricanes, and what's the probability that we will have one of those hurricanes in the southern hemisphere, given that we're only talking about hurricanes? So this is kind of interesting. Letter B, now, if we're in the southern hemisphere and we have a hurricane, over the total number of hurricanes. So southern hemisphere hurricanes, we had 525. Total number of hurricanes, we had 379 plus 525. That's 904 total hurricanes. And that gives me 0.5808, or about 58.1%. One of the common things we talk about happening in word problems is that students will just try and mash the numbers together without reading the problem carefully. You can see, looking at the table and the little marks that I've made in there, we didn't even touch on tropical depressions in the southern hemisphere or tropical storms in the southern hemisphere. In the first part, we didn't look at anything in the southern hemisphere. So we want to choose the data that we are specifically trying to analyze. And I hope you take a second to try and see how the numbers we chose relate to the table and what they were asking us for. The probability to predict whether a hurricane is in the southern hemisphere. Okay, so what's the probability given a hurricane that it's in the southern hemisphere? So there's a lot going on there, and I encourage you to really make a conscious effort in figuring out why we chose the numbers that we did to represent these probabilities. Here's a look at your assignment for section 10.2 here in Algebra 2.